Good afternoon, everyone. My name is Furutan Fami, and I will be presenting optimization of IoT slices in Wi-Fi Enterprise Networks paper to you. I'm a master's student in telecommunication at École de Technologie Supérieure. The outline of my presentation is as follows. We'll start with a brief introduction on the related subjects, then we will move on to the problem formulation where we present a mathematical model followed by an optimization problem. Later, we continue with our proposed solution to find optimal results of the formulated problem, which are of the major contribution of this paper. And we will end the presentation with simulation results and the conclusion part. As you know, we are facing a rapid growth of wireless connectivity, and IoT devices are responsible for a huge share of this growth. Obviously, we need to provide connectivity for them. But how connectivity of these devices are going to affect our networks, and what are the precautions that we need to take before having a stricken with the new wave of the massive traffic generated regarding the IoT devices? Firstly, the IoT environment is full of various devices produced with different vendors all over the world, and not all of them follow the same standard. Therefore, we are facing a highly heterogeneous environment. Secondly, we are dealing with a swarm of heterogeneous devices. It is rational to say that they're built for different applications and use cases. Therefore, they're serving different purposes. And with this manifold, it is obvious that they have a diverse requirements. Let's keep in mind that all these devices require connectivity, and we're talking about indoor environments where Wi-Fi is the dominant technology in terms of exchange traffic. To address the aforementioned challenges, technologies such as software-defined networking and network function virtualization comes in handy, and the most recent paradigm leveraging these technologies is network slicing, which is somehow a virtual network tailored for a specific application or specific requirement in the network. We can say that the most prominent feature of network slicing are improved flexibility by configuring the network and maximize efficiency and provide service continuity. We took advantage of these features by combining the network slicing with Wi-Fi to address the IoT resource allocation problem. We use an architecture in our previously proposed work, which mainly targets an enterprise Wi-Fi network. The architecture has three main components: an IoT platform, which deals with different application services, an IoT broker for QoS aggregation, and a Wi-Fi network manager. Each application involves with different type of devices to provide these applications with the required data. The platform must deal with different networking requirements. It can simply be throughput, or in more complicated scenarios, it can be a bundle of requirements such as delay, jitter, or packet error rate, or etc. IoT devices require communication links to transfer the generated data, and in this proposal, we assume Wi-Fi to be the only communication technology. So access points act as IoT gateways in this architecture. And there is a Wi-Fi controller or Wi-Fi network manager that is in charge of controlling and enforcing network policies and providing the intelligent decisions. So without further ado, let's take a look at the problem formulation. Here we have a main variable x, which is a binary variable corresponding to the associations that we are performing here. Let's define the constraints first here. Constraint 1 defines that the data rate of each device is bounded by its SNR value while connecting to an access point. Each access point has a specific capacity for serving the consumers connecting to it. The achievable throughput for each consumer highly depends on the number of connected devices on an AP and their data rate. So that can be presented in equation 2. And in equation 3, we define the minimum throughput requirement for each IoT device based on the information received from the IoT broker. And equation 4 and 5, they put constraints based on the tolerated delay for the IoT devices that we have and their acceptable packet error rate. So these are defining the slicing constraints that we have in our problem formulation. We assume that the existing network has enough capacity to serve all IoT demands. So constraint 6 makes sure all IoT devices are connected. Constraint 7 guarantees that each IoT device is only connected to a single access point. And constraint 8 allows non-IoT consumers to be de-associated if needed. And constraint 9 defines the threshold for AP capacity. As we know, that access points have some capacity, so the constraint 9 defines that one. We formulate the association problem based on the required bandwidth for each slice and from the optimization problem with the objective of maximizing the overall network throughput. So we call it ISOP, which is NP hard in general due to its binary and nonlinear constraints. We use Groovy Solver to find the optimal association, and it's obvious that in a large-scale problem, using a solver is not preferred due to high computational resources and time required to solve the problem. Therefore, we proposed a new heuristics to deal with this issue. To address the complexity of our optimization, we modeled the association problem as a matching game in which we can consider consumers and access points as two sets of disjoint players. We map our problem to many-to-one matching since each consumer can only connect to a single access point. An access point can match with subset of consumers. So we define different preference lists for each set, and the access point preference is based on associating consumers that have less contribution to access point utilization as long as there is enough resources for accepting these users. And in other words, we can say that AP incentive is for users that have a higher data rate that leads to less airtime utilization. On the other hand, users prefer to associate with an access point that provide higher SNR, which from user preference list, we can see that. So in this association problem, we define extra priority in the preferences for all our IoT devices. It has been proven that deferred acceptance algorithm can guarantee a stable matching in the wireless domain. So therefore, we modified this algorithm based on our problem and use it for our matching. In our modification, we take into account for IoT devices by providing them with the highest priority in the matching. We can basically say that we let the IoT devices to connect to an AP which is nearest to them. And we use an algorithm similar to bubble sort for creating the preference list that we were talking about. Therefore, we can define the complexity of the whole algorithm based on the best and worst case scenario for creating the preference list, as you can see in this slide. The next solution is based on the deep reinforcement learning solution. Generally, reinforcement learning can be applied to all sequential decision-making problems that relies on past experiences. And this motivates us to use reinforcement learning to solve our ISOP that fits perfectly an RL process, especially that an RL solution is considered as a long-term solution that can highly reflect the different dynamics of our IoT network, and it learns its behavior over a given time horizon, and then it can adjust the user association decisions accordingly. We chose a proximal policy optimization model, which is an actor-critic deep reinforcement learning model composed of two neural networks. The actor network decides which action should be taken by calculating the policy, and the critic network informs the actor on how good the action was and how it can be adjusted by calculating the action value function Q. So we can say that PPO is a model-free reinforcement learning algorithm. And the main advantage of PPO is solving the problem of low training efficiency and large policy changes. We model the decision process of our user association as a Markov decision process. This MDP is presented as a tuple composed of finite state space, a finite action space, the immediate reward function, and the discount factor that reflects the importance of the current reward on future decisions. The deep reinforcement learning agent resides in our wireless network manager, and in our modeling, the state space includes the SNR matrix and the consumer's minimum requirements, and our action state presented as the index of APs that a consumer connects to, and the reward function is the sum of the weighted values of the total system throughput, the total AP utilization, and the occurrence of violations for each slice at the time t. So to maximize the reward function, the PPO agent needs to maximize the total system throughput, and which guarantees high system throughput, and it has to maximize the total AP utilization that guarantees high AP utilization and low number of unmatched users. And it has to minimize the number of occurrence of slice requirement violations, which guarantees somehow the QS requirements that we define in our slicing. We conduct a series of simulations with different scenarios to evaluate our proposed solution, in which the number of IoT devices and mobile users varied. So in this simulations, we neglect the interference in our calculations. So also we assume that all devices are using the same transmitting power, and all access points are using the same power profile, which can somehow reflect the results. And looking at the figure on the left, you can see a snapshot of the system that shows our AP placement and how consumers have been associated with different access points. We compared our throughput results with the RSSI beta association. Figure on the right shows this comparison. We can see that our solution outperformed the conventional association approach in terms of total network throughput. Looking at the figure on the left, we can see that our proposed solution performed well in terms of balancing the load on IPs like access point number 13 and 16. We can see that our algorithm tried to balance the load using the available resources in the neighboring APs. Figure in the middle shows the average delay and the significant improvement using our heuristic. And the figure on the right shows how our solutions contribute to the share of resources being distributed among different slices. We can see that using the conventional approaches, the amount of resources that are shared between slices are almost the same, no matter what type of service are being used. While using our solution, we can see that the slices that has services like that need more resources gets what was required here. So to conclude the presentation, we can say that we propose two new heuristics for provisioning the resources of IoT slices in an enterprise Wi-Fi network, considering different requirements of IoT applications like throughput, the delay or packet error rate. Then we formulate the optimization problem for this, and we present a matching-based heuristic that can find the optimal solution in near real time. We also present a deep reinforcement learning approach for the formulated problem using proximal policy optimization model. And we show that our results provide us, we can say that our results show that the proposed solutions are performing as planned and they can meet our system requirements. So I would like to thank my professor here and my colleagues who helped me during doing this studies, and thank for your time and for your attention.